All right. So, hello, this is Mr. Heavener. This is during the pandemic of 2020. That's why I got a mask on. This notes we are doing oxidation and reduction. All right. So we're flipping to the first page. So, if you guys got questions, it's fine. It can be just normal. All right. So we haven't really talked about this last year or your sophomore year, so this is brand new, but the first part of it's fairly simple. We got transferring electrons from one substance to another leads to a flow of electrons, an electric current, thus chemical reactions are used to generate electricity, such as in batteries. So that's a voltaic cell. So we're basically looking at, not yet, but the second half of this unit is looking at batteries, the chemistry behind batteries. And then we're also going to be looking at electrolysis. The process can be reversed, in which electric currents are used to drive chemical reactions. So we're going to be looking at redox reactions that do not occur naturally, but if you drive it by plugging it into an outlet or an electric current, then it can occur. And what is that used for? It's used for like electroplating. That's a very common thing. Like if you have gold-plated silverware, if you have pure gold, that's super expensive, and when you try to like eat, you might bend your fork because it's really malleable gold. So they take stainless steel, which is really nice and hard, cheaper, and then they plate it with gold using electrolysis as their process. All right, so what is oxidation? In a nutshell, oxidation is the loss of electrons. The loss of electrons by an element, compound, or ion. Just cleared up a lot of space on my laptop, so it's still recording. All right.
Yes.
All right, then we got reduction. It's virtually the opposite. The gain of electrons by an element, compound, or ion. I'm just going to do those, what do you call those? Apostrophes? No, quotation marks. Quotation marks. Gain electrons by an element, compound, or ion. And to help you remember this are two mnemonic devices. You can pick your favorite one. We got oil rig. Oil stands for oxidation is loss, and reduction is gain. But if you are more into the environment, you might want to go with Leo the Lion goes grr. And lose electrons oxidation. I'm just doing E minus for electron. And then grr is gain electron reduction. And if you kind of want to see a half reaction, here's some examples right here. We've got A2 minus oxidizes and forms A minus plus an electron. So oxidation is the loss of an electron. All right, and then we have reduction. It's kind of all jumbled here. Didn't convert well. Reduction is the gain of an electron. So right here, A plus is going to form A2 plus plus an electron. That looks like oxidation right there. Which one of these is reduction? Oh no, that's losing. Oh, these are both oxidation. And then, oh my gosh. Yeah, the arrow goes the other way. A2 plus. Oh, okay, got it. Yeah. So when we're gaining electrons, it's reduction. So yeah, it's going with the arrows. And when it's oxidizing, it's losing electrons. You got it. So as we go left to right, it's oxidation, right to left, reduction. All right, so what we got, some quick notes are already written down for you. So some things to remember is anytime you got a monatomic element such as sodium or a noble gas like neon, the oxidation state is 0. And it kind of coincides with what we already know in terms of the noble gases, 0 charge. But if you got a diatomic element, their oxidation state is also 0. So metals by themselves, nonmetals by themselves, and diatomic elements, 0. But then if you have an ion, the oxidation state is the charge of that ion. So like sodium plus ion is going to be a +1. Calcium and anything in column 2 on the periodic table is going to be 2+. Chlorine, halogens are -1 when they're not in a diatomic element, and the oxygen sulfur is -2. But if you look at the periodic table, up there you might be able to see it. Got one right here. And it's all looking like a blur of ink. But if we look at sulfur, is that a 6? That should be, I guess, no, I think that was a 5. No, that's a 6. Okay. So we got 6, we got plus or -2, we got 4. Trillium, we got 4, 8. No, that's a 6. 4, 6, -2. I think that's a 5. But main idea, we got multiple states, oxidation states. So when we're saying things like chlorine, is it always going to be -1? Not always. Not always. There's situations where it could be something else. But the default is going to be -1, the most common form. If it's with a, yeah, well, we'll do some examples. So, number 3, the sum of the oxidation numbers is 0 for a neutral compound and is equal to the net charge for polyatomic ions. So H2SO4, net charge is 0, so the sum of the oxidation states should be 0. So that means hydrogen, there's 2 of them, so 2 times +1, and then plus oxygen, there's 4 of them, 4 times -2, and then there's sulfur, there's 1 of them, I'm just going to put S for sulfur, and this equals 0, which is the overall charge. So 2 plus -8 plus S equals 0. What's 2 minus 8? That's -6. Plus 6 plus 6. Sulfur charge equals +6. You got it. And as you can see, like we were saying that oxygen, sulfur, selenium are -2, but that's not always the case, depending upon what it's bonded with. The 2 big ones typically, hydrogen, oxygen. Hydrogen is always going to be +1, oxygen is always going to be 2 minus. There, of course, is an exception, which we'll get to after this example. So we got ClO4 minus. Cl is unknown, and oxygen is 2 minus, but there's 4 of them. And what's the overall charge? -1. Fun fact, trivia, ClO4, what's the name of that polyatomic ion? Perchlorate. Nice. The gold group on top of it. I had to give it the purple.
Yes.
Well, they're going to be watching this video. Okay. All right. Cl plus -8 equals -1. You guys can't see that. There we go. All right. So then we add 8 to both sides. Cl equals +7 is the oxidation state of chlorine in that situation. All right. Moving on. What time are we out? We're out at 10:25. Okay. Hey, 11 minutes. Nope, that's wrong class. There we go. All right. this there. All right, usual oxidation number for an element is the same as the charge on its most common ion. Group 1 elements have oxidation of +1, group 2 +2. The aluminum column is going to be +3, and so on. That means for many elements, their oxidation state can usually be predicted from the periodic table. Of course, it's not always the case. So we got column 1 is +1. Halogens are typically -1, but not always. Oxygen's always going to be -2 unless it's a peroxide. And the only peroxide you're going to be dealing with is H2O2, in which case the O2 would equal -1. And the reason that is because we're talking peroxide is anything where you got two oxygens together. So that's more organic. So in organic chemistry we would get into that further, but even in this class with organic we don't really get into peroxides too much. Hydrogen's always +1 unless it's in a weird situation where it's a metal hydride. Again, not a common situation, it'd be -1. So if you got positive hydrogen with a positive metal, it's going to act negative. So, chlorine, bromine, -1 unless they're with non-metals, then it gets different. And here we got a bunch of example problems, which is more of what we're doing. So we can do NH4 together. N is typically -3, but maybe not in this situation. So we're going to start with hydrogen. Hydrogen's always +1. There's 4 of them, plus nitrogen, and it equals +1. N plus 4 equals +1 minus 4. Hey, in this case, it's actually the common oxidation state. Nitrogen is -3. All right, and then we got copper. Copper could be +1 or +2. All transition metals are one or the other, or multiple possibilities, except of course like scandium and zinc, which later in the next unit we're going to find are technically not transition metals because they only have one oxidation state. Zinc is 2, scandium is 3. They have to have multiple oxidation states. That's one of the criteria to be called a transition element. But all the transition elements do have multiple oxidation states. So that way copper, we don't know what that is. Until we look at chlorine, we can assume chlorine is -1. There's 2 of them. And 0 is the overall charge of that compound. What did you guys get for oxidation state of copper? +2. Chlorine, so if basically chlorine is always going to be -1 if it's with a metal or a positively charged element. But once it starts bonding with a non-metal, then it could be one of its other possible charges or oxidation states. Key to know, I haven't been paying attention, I've been consistent with this, but if you have a charge in front, +1, that is the oxidation state. If you have something like 1+, that is the charge. So it is purposeful what you put first. I don't believe the IB curriculum is going to ask you any specific questions with that, but that is the difference. All right. Do you guys want to try some on your own?
Yes.
All right, I'll pause the video. So this is the time where you can work on the rest on your own. All right, so here are the answers to 3, 4, 5, and 6. We're going to go quick, so you may have to pause this video. All right, and we're going to do just 2 more things. So the oxidation number is, so we'll fill that in. Here we are. So the oxidation number is the measure of electron control that an atom has, meaning the higher the positive number, the more the atoms has lost control over the electrons. Thus, the greater the negative number, the more electron control an atom has. Maybe next year I'll just print it out for you. All right, and any change in oxidation numbers during a chemical reaction indicates that a redox process is occurring. Increase in oxidation number indicates oxidation, and a decrease in oxidation number indicates reduction. Which is always kind of confusing a little bit. I always think if the charge or the oxidation number is getting smaller, it's being reduced. Or if it's becoming more negative, even though it's gaining electrons, gaining negative electrons. All right, and if you need more time to write that, you can pause the video. Otherwise, that's it for today.